Just when I thought I understood positives and negative electric potentials, I looked at the textbook definition and my goodness, it had such big words like work done by external force, unit positive charge, infinity to that point without accelerating. And I was like, oh my God, what is this? This looks so different than what I understand. But in this video, we'll figure out exactly how we calculate electric potential using work done. And by the end of the video, this statement would have made a lot more sense to you. So let's quickly start with something that we've already seen before. In gravity, if I say potential at a point A with respect to its some reference is 11 joules per kilogram, it means if I were to keep a kilogram of rock, let's say at that point, it would have 11 joules of more potential energy compared to how much it would have at this reference point. Over here, it's the ground. And the same thing applies here. When I say potential at point A with respect to infinity is negative 300 joules per coulomb, it basically means if I were to keep a coulomb of charge over there, a coulomb of charge, let's say at that point, it would have 300 joules of potential energy less compared to when this is at infinity. And we've talked more about this in our previous videos on introduction to electric potentials and potential differences. So if you need a refresher, feel free to go back and check those out. But the goal of this video is to figure out how to calculate these values. How did we know this was positive 11, for example? And how did we know this was negative 300? How did we know it was negative? So how do you calculate these potentials? All right, so to do that, we can go back to our definition one more time. So potential at any point A with respect to some reference is basically how much potential energy that charge has at point A with respect to reference, which in our case is infinity, so compared to the reference per charge, because we are doing it for 1 coulomb. So I have to divide this per charge. And so all I have to do is figure out the potential energy difference. If I can do that, I can calculate the potential. So that brings us to the next question. How do we calculate potential energies? Well, I like to go back to my gravity. How do I calculate potential energy when it comes to gravity? I used to remember the formula, mgh. It was very famous, but I don't want to do that. I want to use concept, basics, fundamentals. So how would I calculate, or what does it mean that my potential energy of 1 kilogram is 11 joules? What does it mean? Going back to basics, it basically means that 11 joules of energy is stored up. And if I were to let go of this stone, as it comes from here to the reference point, which is the ground, it loses all that 11 joules and it gains kinetic energy. So it gains 11 joules of kinetic energy, again, per kilogram, because we're defining it for 1 kilogram. So what I can say is, if I want to calculate potential energy at any point, just let go of that and see how much kinetic energy it gains when it reaches that reference point. Whatever kinetic energy it gained, that number itself should be potential energy, because that must have been stored up. Does that make sense? So let's write this down, because we'll do it step by step, slowly. So what I can say now is this number should equal how much kinetic energy was gained, or I'm just gonna write gain, as it moved from A to reference point. As it moved from A to reference point per charge. So before we continue, let's just hold over here and see if we can use this definition to think about, to realize when we have potential, when the potential will be positive or negative. So when you go from your point, your preferred point to the reference point, if you gain kinetic energy, it'll be positive. And that's why we got over here positive number. As it went from here to here, it gained kinetic energy. But what if this number becomes negative? Then the potential would be negative. The example for that would be over here, if the reference point was above. Now think about it. Now when the rock is going from here to here, first of all, it doesn't automatically go. You might ask, how in gravity rock would go from here to here? How would it go up? Well, you imagine, you didn't drop it, but you imagine you threw it up. That's the trick. You imagine it's being thrown up. Now when it goes up, it slows down, it loses kinetic energy. And so this is negative. And therefore potential over here would be negative with respect to this point. Does that make sense? Pause the video and think about it, okay? Does it make sense to you? Well, yeah. Let's follow the chain of thought. As it goes up, kinetic energy is reducing, meaning potential energy is increasing. Therefore, this point has more potential compared to this. And so this point has less potential compared to this. And so that means this will be negative potential. So it makes sense, right? Same thing happens over here. Now, can you pause and convince yourself why over here we'll get a negative number? Pause and try. All right. If I were to let go, does it go to the reference point infinity automatically? No, it gets attracted. So I throw it away just like over here. And when I do, what happens to its kinetic energy? It reduces. Because it's of the attraction, it reduces. And if kinetic energy is reducing, you get a negative number here. That means the potential is negative. And see if it makes sense. Follow the chain of thought. If the kinetic energy is reducing, that means potential energy is increasing. So at infinity, you would have maximum potential energy. And so the potential energy over here would be less compared to that of infinity, giving you a negative sign. Okay, but now we can dig one step deeper and ask, hey, but how do you calculate this? How do we calculate how much energy, how much kinetic energy is gained or how much kinetic energy is lost? How do you calculate that? And for that, we use our work energy theorem, something that we may have learned a long time ago. Work energy theorem states work done equals gain in kinetic energy. So what I could write over here, the gain in the kinetic energy would be same as the work done by which force? The force of gravity here, or the force of electricity. So I'll just write force of electricity. Work done by the electric force in moving it from point A to the reference point. And again, per charge. And again, let's come back over here and see if it makes sense. So if I want to calculate how much potential energy I have over here, I need to figure out how much kinetic energy is gained or lost as it goes from here to here. But to do that, I have to calculate how much work gravity does in moving it from here to here. And how do you calculate the work done by gravity? Or how do you calculate work done by any force? You calculate it as the force multiplied by the displacement. So all you do is figure out how much the force of gravity would be. So maybe the force of gravity is downwards. Multiply that by the displacement, how much the displacement would be, and that number would tell you how much kinetic energy is gained, and that number would tell you how much potential you would have. And the same thing would apply here as well. If you want to calculate how much potential you have at this point, figure out how much work is done by the electric force. In this case, the electric force is downwards, but you move it all the way to infinity, so you have to move it in the opposite direction. So this is the electric force. And in doing that, figure out how much work is done. Now you might say, hey, but infinite distance means, is it infinite work? No, because remember over here things get a little complicated because as you go away, the force itself starts changing. And so you can't just multiply force and displacement, you'll have to integrate it. And something, don't worry, we'll not do this in this video, we'll do it in a future video, but you get the point. And notice over here, work done by electric force is negative as you go from here to here. And we already knew that because it's negative, we're gonna get a negative potential. Now, actually, we are pretty much done because we now found a way to figure out potentials. All we have to do is calculate work done by the electric force in moving it from that point to infinity per charge, and we're done. But sometimes you will also have external forces acting on you. And so there's another way to define electric potential in terms of work done by the external force. Let me just introduce that because your textbooks tend to do that. It's not necessary. You don't have to do it. I don't usually use that at all, but let me do that anyways. Let me just define it anyways so that things are clear. Let me just get rid of this. All right. Imagine that when we're moving this rock from here to here, imagine we're not just dropping it. Let's say we are holding it in our hand and we are slowly moving it down. Slowly and steadily, without any acceleration, we are moving it down. Then my external force, the force that I'm putting on the rock, would be upwards. Let me write the external force with this color. Okay. This would be the direction of my external force. This would be my external force. Does it make sense? Because if it was not upwards, it would just fall down very quickly. I want to move it slowly without any acceleration. Then see what would happen. then my force would exactly equal the gravitational force, but it'll be exactly negative. And so the work that I did would be exactly negative of the work done by gravity. So I can also say, and the same thing would apply here. Okay, even here, what I could do is instead of throwing it and just allowing it to go slowly, what I could do is I could put an external force in the opposite direction, exactly equal to the electric force. This is the external force, and slowly, without any acceleration, move it from here to infinity. And in doing so, the work that I did would be exactly opposite of the work that electric field did. And so now I could also say that this is also equal to the negative of the work done by the external force in moving it from point A to the reference point. Does that make sense? Per charge. Per charge. Where is that? Okay, per charge. All right, but there's a caveat. There's a small detail. I have to move this without any acceleration. So conditions apply, no acceleration, because if I accelerate, let me show you. If I accelerate, then my force will not be equal to the electric force. Then my work done will not be equal to the work done by the electric force. Then this will not hold true. So only if I do it without acceleration, the two forces will be equal and opposite, and my work done would be exactly equal to the negative, but in number exactly equal to the electric force. So I can also use this definition. So I can also say potential at a point, I can also say it is the work done is a negative of the work done by the external force in moving it from that point to infinity without accelerating. Finally, what your textbooks do is they say, look, I don't want to define in terms of negative, so how do I get rid of the negative sign? And the way to get rid of negative sign is actually quite simple. See, if you do, when you are moving things down, if you're doing a negative work, then when you move things in the opposite direction, you will do positive work, right? So instead of moving it from A to R, you move it from R to A, and then the negative sign will go. So let me just write that down. We can also say this is equal to work done by the external force in moving it from R to A per charge. And I know it's a little crowded, so excuse me for that. And these two are the same things. And let's see what this means. This means, if I start with gravity because it makes sense, it says if you want to calculate potential at any point A, find out how much work is done by an external force in moving it from ground to that point per kilogram. Does that make sense? Yeah. If I want to find out how much potential over here is, take a kilogram, move it from the reference point to that point A, and whatever work you did, that will be stored as potential. That makes sense, right? The same thing applies in the charges as well. And that's why your textbooks define it as potential at any point with respect to infinity. They don't mention that, but that's always with respect to infinity, equals the work done by the external force in moving a coulomb of charge from infinity to that point without any acceleration. And now I know there is a lot of things introduced, so it's going to take some practice to get used to it, but we now have so many different ways of calculating potentials. My favorite is just doing this. This is literally my favorite. This is the easiest. I don't have to worry about external forces, but yeah, you can use these definitions as well.